Okay, if you speaking of stack frames, okay, so if you go way back in time, if we go back in we'll take a like like a trip in the Wayback Machine. Years and years and years ago, you had what was kind of termed a dedicated operating system. It usually meant you could only run one application at a time, like in the days of DOS, back like before, like I think before Windows 95, back in the 80s, back in the 70s. And some of your mainframes, which were really large back then, did have multitasking, but it was limited. And then, so imagine to try to kind of explain it in a way, imagine you've heard of the kernel. I'm not sure if you've heard of a kernel, but a kernel is the core part of the operating system. So if you take a moment and kind of just look at your computer, right? Your computer only has, I mean, it can have more than one, but it only has one keyboard, one mouse. So how do you, when you're typing something in or you're moving the mouse, how do you know what to interact with? So that's one of the first questions. But the kernel actually, without going into all the different layerings of the operating system, the kernel would be responsible, let's say, for that very basic function of reading the keyboard input. So let's say you type in the letter K. We'll do it over here like in this Notepad++. So let's say that I'm going to type in like this is a test, right? So it's up here. And I'll bring it down a little bit. So the kernel would be responsible for taking the keyboard input. Now, we're not going to complicate it with different keyboard mappings or character mappings or nothing like that. It's just a piece of hardware. Think of a keyboard. It's just a piece of hardware. Whenever you type a letter, I believe it serially transmits the data. So let's say a K, for example, is 8 bits, so it would be 1, 2, 3, 4, 5, 6, 7, 8. But it may be represented as example of, like, let's say a BC, and there's a way, or BC, not GC. But let me show you that real quick. So we'll go up over here, and let's do, they call it we'll do it ASCII table. It's the good old ASCII table. So let's see, here we go. So this is what I mean. We'll make this bigger. So the letter K to the computer would be 4B. So 4B is the hexadecimal representation of, let's say, the letter K, and that's using an ASCII table. So when it reads that character, what does it do with it? I mean, I've got an application back here. I've got this going. I've got other programs running. If you take a look at Task Manager, you can see that there is a lot of applications running over here. You have services running in the background. You have a lot of different things all in here. So how do you know where the input goes? Well, the way that the kernel, to me, the way that it decides, especially if you have like sorts of like a keyboard, unless you're directly reading that device. Now, the code used to years ago, the keyboard, you could add, the keyboard would, and the mouse would be registered to what they call a port on your computer, and you have a chip, a computer chip inside that can receive data from that port. It's just like an old joystick, the old like Atari joysticks. They're just switches, and depending on which switch is on, like if you're going diagonal, you have two switches on. Like diagonally to the left would be left and up. Those two switches would be on. So when you read that register, when you read that memory location, which is a chip register, it'll return a certain value. And then you could say, oh, that value means that I'm moving upward to the left. And then that's how you can draw your graphics. You can adjust your graphic positioning to move your sprites or your images or your screen if you're scrolling. So how does it know what to do? Well, if you notice, if I type in over here like a Control S, it sent the Control S to this application. But if I go over here and type in Control S, it's going to want to save it. So, sorry, how does it know the difference? Well, the only way they can know the difference is what application has focus. The way that Windows and other multitasking computers, the technique they use is what has focus. So if you're not reading the register directly, you have to rely on the operating system. So when you press a key, the operating system creates a message. It says this key was pressed. All right, who has focus? Which application is waiting for input? So if I'm clicking on this application is waiting for input, but I can get input from this list, all of these are considered separate controls. Windows calls them controls, but these controls can receive different forms of input. And input can be scrolling. See, I'm scrolling the mouse, but notice this over here isn't moving, but now I'm scrolling this because now this has focus. This now has focus. This has focus. So it's where a kernel, which is not multitasking in and of itself, can then give the illusion or share its non-multitasking environment to a multitasking environment, to go from not multitasking to multitasking. So all of that is an illusion because you can have different threads and different cores, but it's still kind of illusion because only certain things can be done one at a time. Okay, so that kind of gives you the idea of multitasking. But what happens when you multitask? Well, if you have a lot of applications running, who do you give priority to? So I've got this application running here, and then I've got this application back here. So who do I give priority to? One technique you can do is whichever application has focus, you can then up that application's priority and downgrade everything else's priority. But you can do that. That's one way to do it. And then you could put priority for any type of input device. But that's kind of built into the hardware because what they have is called it's called an interrupt. It's like an interrupt service. So whenever a hardware chip says I've got data, because like a serial chip, a normal serial chip, it's a chip in a computer that reads 1 bit at a time. Old printers used to use serial. Keyboard is serial. USB is serial. It transmits 1 bit at a time. So it has to know when it's got a byte or a frame. The UART chip, which is the old serial chips, they only could hold 1 byte of data. There was no buffer. So you got data coming in. Like you've got constant data coming in. So once that little byte gets full, they have to do what they have to do what's called a hardware interrupt. They signal the processor, you need to deal with what I've just read or what I've just read in, because if you don't, I'm going to overwrite that and you're going to lose your data. So in other words, you might print out a report, or your mouse may move erratically, or something may just not work. You may have a USB device constantly reboots because the communication between the two devices, the computer and the USB, is somehow getting jumbled. So it gives the illusion of multitasking. So what you have is time slicing. How do you time slice something? Well, you can allocate so much time for each application. And you could even change that based on priority. You can say, okay, I'm going to give this a higher priority, so it's either going to have a larger time slice, or it's going to have more of a time slice, or it's going to have a longer time slice, or I'm going to give it more individual slices. Or you can have what they call preemptive. So preemptive means that whenever this thing, you could say that whatever I'm about ready to execute will preempt something of a lower priority. So if a higher priority task needs to run and a lower priority task currently has the CPU, it'll preempt the one that it needs to run, the higher priority one, over the lesser priority one. So it kind of puts it on a back burner. It stops it, it saves whatever registers, and then it executes the higher priority task. So now we're into scripting. So in scripting, what you have is it's a program. So you're typing in this code, and the compiler translates it into, I believe it's executable code, if I'm not mistaken. You can either have bytecode, which is an intermediary language where you have like if x equals 1, do this, but the bytecode might say 5b or like a 5b 1 3. So it might take 3 bytes of bytecode where it takes much longer to actually parse that line out. So like a B3 might be greater than, B4 might be equal to. So it says, okay, I know I'm doing it equal to, the next byte is the first letter, next byte, or word if it's a very large number. But it crunches everything down, and it makes executing fast because it knows, like a bytecode knows exactly how big the parameters are, and it can instantly jump to the next chunk of code. All right, so that's what the Papyrus does. So it takes that scripting that people write, and it's basically a piece of code. So coding is like logic. You're a logic translator. You're taking something that somebody says logically, this should happen in this order, and you're taking those step by step. Each step. I'm trying to think how to put this. You're taking each step in that order, and then you're translating that step into code. So you can say, if my if I have $10 in my wallet, spend it. So you can create a variable and call it wallet and say, if wallet greater than 10, do this. Else print not enough money. And then you can so you have like a program, a chunk of programming code or like scripting code. But when you have a very large scripts, if I understand it correctly, what the game engine does, it allocates a very small slice of time for every frame it displays. And normally you display like 60 frames a second. So when your frame rate drops, your scripting is going to drop, because normally scripting runs in between those frames. So if you're only doing 30 frames a second, your scripting is only running 30 times a second. But what it has to do, it has to execute, like let's say you got 100 scripts running. It has to execute or try to execute as many of those 100 as it can in that time slice. So instead of trying to execute the whole script, it will only execute part of it. And that can be called a stack frame. So a function call can be called a stack frame. So if you have a function that adds two numbers together, and then you have a function that subtracts two numbers, like hit points, let's say. You get shot with a bullet, you're going to have to figure out who did the shooting. You're going to have to take the bullet, and you're going to have to back reference it to the NPC that it belongs to, who it hit, what type of ballistic it is. Those are all references. They're linked together. And once you know what the data structure is, then you can figure out who fired the shot, and therefore you know it's an enemy or friendly, and that's kind of like how it knows. But if that's too much to execute, you have to break that down into frames. So Papyrus can only execute a very small portion of that script, and it remembers what it did. So then it kind of puts that on the back burner, and then it executes the next little chunk of a script and puts that on the back burner. And that's why when you have a lot of scripts, and really large scripts, that let's say at the beginning of the script it does one thing, but you don't really notice it until the script reaches the end of what it's doing, but it's big. It may take quite a few slices of that script to get down to the bottom. So you have what you perceive as script lag. It's like the script is not acting fast enough. That's why when you have very few scripts that are very small, they have very few frames. It breaks it down into very few pieces. So it seems to be more responsive. Or if you can get your frame rate up high enough by lowering your graphics, lowering your resolution, a better graphic card, faster memory, things like that, get better throughput on your system bus, then your frame rate is going to go up, and therefore your scripting seems to improve. So what a script frame is, it's a small chunk of a script that gets executed, but then the Papyrus, the thing that's doing all the interpretation of it, puts that on hold, and then it executes a chunk of the next script. And this happens so fast that it looks like all of these things are happening at the same time, but they're not. They're all happening sequentially. So if one of those frames, if you go into Resaver and you delete one of those stack frames, it's either going to throw Papyrus off because it's going to say, wait a minute, I'm expecting to go back to a particular frame. It's not there. And I'm going to crash with a virtual, I'm virtually confused because I don't know where I'm going now because the frames are missing. Like I say, or you can get it can choke the Papyrus engine. So it means you're going to get script lag. So that's kind of like how that is. I hope that helps some. If not, just holler at me and I'll see if I can try to maybe explain it a little bit better. But that's what a frame is. It's a small piece of one individual script. That's all the engine could execute, because you basically tell it, this is how many microseconds I'm giving you. They call it a tasklet. But this is how many microseconds I'm giving you to get this frame done. And if you can't get it done in that time, I'm putting you on hold. And like I say, that's what gives that illusion of script lag. So I hope that helps, and just holler if you need anything else.